March 2014, 30 miles off the coast of Florida, a hydrophone array picks up a sound so violent that for a moment, the engineers monitoring it assume their equipment has failed. It wasn't a submarine. It wasn't an earthquake. The source was smaller than your thumb. The array in question was part of a passive acoustic monitoring network, the kind of equipment normally used to track submarines, log seismic activity, and eavesdrop on whale communication across entire ocean basins. These systems are built to withstand extremes. They're calibrated for the deep boom of a container ship's engine, the low-frequency call of a blue whale traveling for hundreds of miles, even the occasional distant rumble of an underwater earthquake. What they are not built for is what showed up on the recording that day. The reading spiked to over 200 decibels at the source. To put that number into perspective, a jet engine at close range measures around 150 decibels. A gunshot, close enough to cause permanent hearing damage, measures around 160. This reading was recorded at a source smaller than a human hand, and it wasn't a one-time event. Similar spikes have been recorded in waters off Australia, in the Mediterranean, in the Gulf of Mexico. Anywhere warm coastal water meets the kind of rocky, sandy seafloor divers describe as sounding like a frying pan full of popping oil. When researchers finally traced the recordings back to their source, they didn't find a machine, a geological event, or a large predator. They found colonies of animals barely 2 inches long, clustered along oyster beds and coral rubble, going off almost constantly, day and night, like a factory floor running at full capacity. And when marine biologists began recovering footage from cameras dropped near these sites, they didn't just capture sound. In several recordings, they caught something recorded at the exact same instant, a flash of light and a spike in temperature in the open ocean, with no external light source anywhere nearby. So here's the situation on the table. Somewhere along the seafloor, something just 2 inches long is producing a sound close to 220 decibels, a flash of light with no visible cause, and a heat signature that shouldn't exist in cold seawater at all. Before we can explain what's actually happening, we need to understand exactly which rules of physics and biology this scene appears to be breaking. To understand why this reading is so strange, you first have to understand how sound works underwater, and what the biggest, most powerful animals in the ocean are capable of by comparison. Sound travels roughly 4.5 times faster underwater than it does through air, and because of that, marine animals that rely on sound have evolved some genuinely enormous capabilities. The blue whale, the largest animal to have ever existed on this planet, produces calls that can reach around 188 decibels, loud enough to travel for hundreds of miles through open ocean. Sperm whales use powerful clicks, some measured above 200 decibels, to locate prey through echolocation in complete darkness. These are the loudest confirmed sounds produced by any animal on Earth, and they come from animals that weigh tens of tons, animals with massive lungs, enormous vocal structures, and body sizes specifically built to generate that kind of acoustic power. That's the baseline. Size and power are supposed to go hand in hand. A bigger animal has more mass to move air or water, bigger resonating chambers, and more raw physical force behind whatever sound-producing structure it's using. It's the same reason a bass drum is louder than a snare, and a lion's roar carries further than a house cat's. Under normal biological rules, a 2-inch animal shouldn't be capable of generating a sound anywhere close to what a 90-foot whale can produce. And there's a second rule this scene appears to violate. Light and heat in the ocean are almost always tied to external sources. Bioluminescence exists, but it's a chemical reaction, cool to the touch, and it never comes paired with a heat spike. Deep-sea hydrothermal vents produce heat, but that heat comes from geological activity, not from a living animal's body. Nothing in standard marine biology accounts for a small, soft-bodied invertebrate that generates light and heat as some kind of biological byproduct, in open water, on demand, repeatedly. So we have two seemingly impossible readings stacked on top of each other: a sound wildly disproportionate to the size of its source, and a flash of heat and light with no external cause. At this point, every serious investigation needs a suspect list, so let's walk through the competing explanations, one at a time, and see which ones survive contact with the data. Suspect 1. Equipment malfunction. This was the first explanation engineers reached for, and it's a reasonable one. Hydrophones can spike from electrical interference and false positives happen, but this theory collapses almost immediately once you look at the data. The spikes weren't isolated to one piece of equipment. They were recorded independently on different hydrophone arrays in different oceans over multiple decades, and they always traced back to the same kind of location: shallow, warm, rocky, coastal water. A malfunction doesn't repeat itself with that kind of geographic consistency. This suspect is cleared. Suspect 2. Seismic activity. Underwater earthquakes and geological shifts absolutely produce sound, and they can produce it suddenly and violently. But seismic events show a completely different acoustic signature. They register as long, low-frequency rumbles that build and fade over seconds, sometimes longer. What investigators were seeing instead was a sharp, instantaneous spike, on and off in a fraction of a second, repeated constantly, sometimes multiple times per minute, from the exact same tiny cluster of locations. Earthquakes don't behave like that. This suspect is cleared. Suspect 3. A large predator, like a sperm whale. Sperm whales are, after all, the only confirmed animal capable of producing sounds in this general decibel range. But sperm whales hunt in deep, open water, not shallow oyster beds 30 feet down. Their clicks also have a completely different acoustic fingerprint, long trains of clicks used for echolocation, not the single, sharp, explosive pop recorded at these sites. And critically, sperm whales don't produce a simultaneous flash of light and heat. Whatever this is, it isn't whale-sized, and it isn't whale-shaped. This suspect is cleared. Suspect 4. The mantis shrimp. This one deserves real consideration because the mantis shrimp actually is capable of something eerily similar. Its spring-loaded club strikes 50 times faster than a human blink, hard enough that the strike itself can, in isolated lab conditions, generate a cavitation bubble and a brief flash of light and heat. On paper, that sounds exactly like what we're looking for. But there's a problem. Mantis shrimp are solitary hunters. They don't cluster into dense colonies, and they're not the dominant sound source recorded at these specific coastal sites, which were absolutely packed, wall to wall, with a completely different, much smaller animal. The mantis shrimp is a real suspect for a similar phenomenon elsewhere, but it's not the source of this particular scene. Close, but cleared. That leaves us with one suspect still standing, one that nobody expected to be capable of any of this. A crustacean barely 2 inches long, found in massive colonies along the exact seafloor habitats where these readings kept originating. It's known by 2 names, the snapping shrimp and the pistol shrimp. Here's what's actually happening, and it comes down to one modified claw. One of the pistol shrimp's 2 claws is dramatically enlarged, and it has a mechanical latch built into its joint, a piece on the top half that locks directly into a hollowed socket on the bottom half. The shrimp uses its muscles to build up tension against that latch, tension so extreme that it actually deforms the shrimp's own exoskeleton in the process. Then, in an instant, it releases. The claw snaps shut in under 2/3 of a millisecond, and that snap forces a jet of water out through a tiny opening at incredible velocity. That jet of water doesn't just push through the surrounding water, it tears through it, creating a swirling vortex ring. And right at the center of that vortex, something remarkable happens. The pressure drops so low, so suddenly, that a cavitation bubble forms, a pocket that for a fraction of a second contains essentially no liquid water at all. That bubble is inherently unstable, and it collapses almost instantly, with water rushing back in from every direction to fill the void. That collapse is the actual source of the sound, a shockwave of pressure so intense it can rival a gunshot, and it's powerful enough to stun or outright kill the small fish and crustaceans this shrimp hunts. This single mechanism also explains the flash of light and the heat spike recorded by underwater cameras. The collapsing bubble briefly reaches temperatures approaching the surface of the sun in a process called sonoluminescence, and it does this every single time the shrimp fires its claw. And there's one more detail that makes this whole system even more remarkable. The shrimp itself is not immune to its own weapon. To survive repeatedly detonating a sun-hot shockwave inches from its own body, the pistol shrimp evolved a thin layer of water positioned between the outside of its head and its brain, acting as a built-in shock absorber against the very force it's generating. So the animal responsible for one of the most extreme acoustic events recorded anywhere in the ocean isn't a whale, a submarine, or a geological event. It's a 2-inch crustacean that solved a problem of pure physics by weaponizing a bubble. And it isn't even alone in that solution. The mantis shrimp, an animal that isn't even remotely related to the pistol shrimp, arrived at almost the exact same cavitation trick through a completely different mechanism, one for hunting power, one for pure acoustic warfare. 2 unrelated evolutionary paths converging on the same extreme physics independently in the same ocean. What's genuinely unsettling about this case isn't the shrimp itself, it's how long it took us to solve it. These sounds were recorded, misidentified, and quietly filed away for years before anyone connected them to an animal most people have never even heard of, hiding in plain sight in shallow coastal water we walk past every single day. If something this powerful, this strange, and this measurable could go unexplained for that long in water 30 feet deep, it raises an uncomfortable question about everything we haven't measured yet in water we can't reach at all. If you found this investigation as fascinating as I did, let me know in the comments, and I'll see you in the next one.